Okay, Bismillahirrahmanirrahim. Today our group will present about research paper 3, that is Color-Stator PM, axial Color-Stator permanent magnet axial field synchronous machine for small scale wind application. So for the introduction, this research explore the design procedure for a Color-Stator permanent magnet PM axial field synchronous machine tailored for small scale wind application, such as axial field machine recognized for their high power to weight ratio and reduced noise. And it also offer promising potential for renewable energy system and particularly wind turbine operating at lower scale. And this design addressed the lack of comprehensive and efficient methodologies for this machine by proposing a streamlined approach combining analytical model and data curve derived from 3D finite element method. And this enabled the designers to bypass the high computational demands of traditional methods while ensuring accuracy and efficiency.
Problem statement. Synchronous machines are fundamental in power system due to their versatility and applications such as renewable energy generation, industrial drives, and electrical transportation. Axial flux permanent magnet (AFPM) machines are a specific types of synchronous machine and particularly suited for small-scale wind applications due to their high power-to-weight ratio and compact design. However, designing AFPM generators could lead significant challenges because traditional approaches heavily rely on 3D finite element method simulations, which are computer, computationally expensive and time-intensive. Additionally, the lack of generalized and trusted analytical formulas limits efficient design practice and widespread adoption. This study addresses these challenges by proposing a detailed design procedure that integrates analytical formulations with 3D FEM-based data curves, aiming to streamline the design process and enhance its feasibility for small-scale wind application.
There are four methodologies that we have in the researchers paper. So the first one, analytical modeling. The researchers derive fundamental equation for key parameters like dimensions in the voltage and torque. This equation establishes the foundation for selecting the machine's dimensions and ensuring balanced multi-phase voltage. For the second one, simulations. They employ a 3D finite element method simulation to validate the analytical models. This method was crucial for optimizing magnetic circuit dimensions, analyzing field distribution, and creating data curve. This data curve reduced the need for iterative simulation, significantly speeding up the design process. For the third one, experimental validation, a prototype was built based on the proposed design. Testing showed remarkable consistency with simulation predictions, with less than a 3% deviation in the output voltage. This confirmed the robustness of the procedure in real-world applications. Lastly, data analysis, harmonic analysis helped optimize the coil span, reducing distortion by 62%. Performance metrics like copper losses, mass, and inertia were calculated to ensure the design met the efficiency and lightweight requirements for wind turbines. In conclusion, the integration of these methodologies, modeling, simulation, experiments, and data analysis, resulted in a simplified yet highly accurate design process. This procedure is scalable and can play a pivotal role in advancing small-scale wind energy systems.
Okay, next we move to our findings. So for the first, suitability for small scale wind application. So for the problem, this application lack of efficient design procedure. This is because the traditional axial field machine rely heavily on 3D FEM simulation for design and optimization. So this approach demand high computational power and significant processing time, making it impractical for widespread use in small-scale wind application. So for the solution, this research introduced a comprehensive design methodology for coreless PM axial field synchronous machine. This procedure combined analytic formulations and normalized data curve derived from 3D FEM result. And the impact, the lightweight and coreless design will reduce the noise, vibration, and ensuring practical deployment in small system. And the validated design also reduce harmonic distortion by 62%, achieving efficient energy conversion even in low wind speed region.
For findings, I'll be discussing the efficiency and power loss management in our coreless axial flux machine design. For problem, efficiency is a critical factor in electrical machines, yet traditional designs face three major types of power losses. First is ion losses caused by magnetic fields in the stator core, leading to energy waste through hysteresis and eddy current. Second is copper losses arising from the resistance in windings, which increase with higher current. And thirdly is eddy current losses, especially prominent in coiled designs where alternating magnetic fields directly affect the windings. These losses can significantly impact the performance and reliability of small-scale wind generator, making their reduction essential. For solution, our approach tackles these challenges through a cordless construction which offers several advantages. First is elimination of ion losses. By removing the stator core, we inherently avoid hysteresis and eddy current losses. Second is reduction of copper losses. Through precise calculation and optimized winding design, we ensure that copper losses are well managed. Thirdly, control of eddy current losses. We use analytical methods and harmonic analysis to keep these losses minimal. For the impact, the results of these designs are impactful. First, efficiency. Without iron losses, the overall efficiency improves significantly. Copper losses account for only 16.6 of percent of output power, which is acceptable for small-scale systems. Next, eddy current losses reduced to just 1.17% of output power, further enhancing performance. And lastly, improve reliability. The absence of a laminated stator core eliminates risks like overheating and saturation, making the machine lighter and more dependable. In summary, this innovative design effectively minimizes losses while enhancing both efficiency and reliability. Is an ideal solution for small-scale wind applications, ensuring high performance with minimal energy waste. Note that for the highlight code, uh, as the machine under study has ironless and slotless stator construction, the main flux would penetrate through the space of the winding. The calculated value of the eddy current loss in stator copper windings of the manufactured prototype machine is 3.52 watt, which represents about 1.17% of the rated output power.
So for the third finding, harmonic reduction through coil span optimization. So for the first one, the problem statement. In concentrated winding machines, the coil span, the physical distance between two sides of a coil, plays a critical role. If the coil span is improperly chosen, the voltage waveform becomes distorted, leading to high total harmonic distortion (THD). For example, in this study, a coil span of 15 degrees resulted in high THD of 56.37%, significantly degrading the power quality. And for the solution of that problem statement, the researchers propose an optimized coil span selection based on the geometry of the machine and the alignment of coil sides with magnetic poles. The key guideline is that each coil side must align with alternating magnetic poles to ensure continuous voltage buildup. Using this approach, the researchers recommended selecting the coil span within a range derived from the magnet's pole pitch and width. For the results, which is the impact of optimization was remarkable. By adjusting the coil span to 45 degrees within the recommended range, the researchers reduced the THD by 62%, bringing it down to 21.37%. Additionally, the fundamental voltage component increased by 44%, transforming the waveform into a near pure sine wave. This improvement not only enhanced the generator's output power quality but also improved overall system efficiency. So, for the conclusion of these findings, this finding underscores the importance of coil span optimization in electrical machine designs. By applying the researchers' guidelines, we can significantly reduce harmonic distortion, improve power quality, and boost system efficiency.
Let's start with the strength of this design. First, efficiency and reduced losses. The cordless design eliminates iron losses, which significantly improves the machine overall efficiency and reduces heat generation. Additionally, the solid bed iron construction simplifies manufacturing, making it less complex compared to other designs. Next is its compact and lightweight nature. The cordless stator construction not only reduces the overall weight but also makes it ideal for wind turbine applications, especially where minimizing mass is crucial to reduce stress on the turbine structure. Finally, we have enhanced performance. This design offers a high power to weight ratio and the flexibility to adjust the air gap as needed. Moreover, by optimizing the coil span, the machine can produce balanced multi-phase voltage and reduce harmonic distortion, thus improving power quality. Now let's look at the limitations. First, there's a dependency on permanent magnets. Coilers design require more permanent magnet material compared to their core counterparts. While this improves performance, it increases material costs. Next, we face higher manufacturing complexity. The precision required to construct a coilless stator and ensure the air gap is correct can pose significant challenges, particularly for mass production. And lastly, harmonic content. The need for meticulous coil span adjustment to minimize harmonic distortion in output voltage.
Okay, next we move to the next slide, that is benefits and impact. So for the first benefits, efficiency and resource conservation. First, the collar stator design reduce the iron loss, improving energy efficiency and lowering the operational cost. Next, the lightweight and simplified construction will minimize the material usage and enhance transportation and installation ease. This will contribute to a smaller carbon footprint. For the next benefits, promoting renewable energy use. By optimizing generator design for small-scale wind turbine, this work supports the adoption of wind energy, a clean and renewable source, and is also reducing the reliance on fossil fuels. And lastly, the scalability and versatility. The flexible design can be adapted to medium and large scale application, so it will broadening its impact in sustainable energy transition.
For the potential future directions, we have three. First, optimization techniques for design dimensions. Advanced algorithms like genetic optimization and machine learning can refine design parameters significantly reduce reliance on time-intensive 3D FEM simulations. This will streamline the design process and improve accuracy. Second, extension to medium and large-scale applications. While our study focused on small-scale machines, adapting the methodology for medium and large-scale machines could revolutionize industrial application from heavy-duty wind turbines to electric grades by addressing scalability challenges. Finally, exploration of alternative materials, research into rare earth-free magnets, innovative rotor and stator materials could enhance machine efficiency, lower cost, and reduce dependency on scarce resources, paving the way for more sustainable designs.
Lastly, for the conclusion, this research present an innovative and efficient design procedure for collar stator PM axial field synchronous machine specifically optimized for small-scale wind application. By overcoming the limitation of traditional 3D frame-dependent methods, the study introduced analytical formulation and data curve, enabling precise and accessible design with reduced computational demand. The lightweight, compact construction, high power-to-weight ratio, and reduced noise and vibration make this machine ideal for low wind speed conditions, while the reduction in harmonic distortion enhance energy efficiency and power quality. This validated through simulation and experimental prototype. The proposed method offers a scalable solution for renewable energy system, aligning with sustainability goals and advancing the viability of small-scale wind energy technologies.